Hey everyone, we're going to jump right into some 5.4, which is the applications of right triangles. Woohoo, word problems. So the first thing we got to talk about are significant digits. And that's because in most trig applications, we're dealing with measured values that are not necessarily exact. So there'll be rounding involved and that sort of thing. So a quick example here, example number 1. Suppose a surveyor measured the road frontage of a parcel of land and obtained a distance of 34.41. I mean, how accurate is that measurement? Most likely, the surveyor did some rounding. I mean, it might be exactly 34.41, but it could be a little bit off of that. We don't know. More precisely, like based on that result, the distance must be between a little less, 34.405, right? And a little above it, 34.415, okay? And so that next paragraph, the results of these physical measurements are only approximations, right? And it depends on the precision of the instrument and who's doing the measuring. But digits obtained by actual measurement are called significant digits, okay? So oftentimes you're talking about the number of significant digits in the measurement. Like this number up here had 4 significant digits. Here's some examples. The significant digits are in red. So this one has 3 significant digits. That one has 3. This one has 4. I mean, if somebody said the measurement is 18.00, they're saying that they were accurate to the hundredths place, right? Because if they weren't, they wouldn't put the 00 there. They would just report 18. So same with this one. Those extra 2 zeros is showing the accuracy to the thousandths place, right? This only has 2 significant digits because the zeros in front don't count as significant, okay? Same with this one. So this one would have 4. And then this one, there's only 2. So the zeros at the end of the number, we're going to make the assumption that this measurement was rounded to the nearest hundredth. I mean, hundreds. Okay. I mean, it may be that it was exactly, but it's a little bit unclear. So we're going to assume the more likely possibility of it being rounded to the nearest hundred, rounded to the nearest hundreds. Okay. So just a quick set of examples, how many significant digits are in each one. So that one would be 3, right? This one would be 3, okay? This one would be 4. Even those zeros in the middle, they're trapped in the middle, they're significant. They were found by the measurement. This one, the zeros out front don't count, so it's just the 6 and the 3, right? This one, the zero, number 6, the 0 out front doesn't count, but the 2 behind do, so that would be 3 as well, 0.500. However, the last one, which does not have a decimal, we're going to assume that those zeros are not significant. This one only has 1 significant digit, okay? So in some problems, you're going to be asked to round your answer to the correct number of significant digits. And then so this paragraph is pretty important for that. I don't want to erase it. I want to highlight it. To perform calculations, first, you're going to identify the value with the least number of significant digits of the given values when you have to do a problem, right? And then you're going to round your final answer to the same number of significant digits as that least number, okay? So that's because your answer can be no more accurate than the least accurate number in your calculation, okay? Now, when you get to angles, I would refer to this table as far as significant digits because angles gets a little bit different with like minutes and seconds and that sort of thing. So we'll refer to that in problems when we get to it, okay? So let's jump to some problems. The problems that we're going to first encounter is solving right triangles, okay? So as long as you're given a little bit of information about the right triangle, you can solve it. Solve it means you find all of the measures of the sides and the angles. We're always going to use this general triangle. If the triangle is not given as a picture, it only gives you A's and B's and C's, refer to this triangle here, okay? In other words, big angle A is always opposite the little side A. Right? So notice A is opposite A, B is opposite B, C is opposite C. Capital C is always a 90-degree angle because we're only doing right triangles, no other type. Okay. So we can always draw the triangle with that picture. So an example, let's solve the right triangle ABC where A is that angle and C is 10.7. Give all answers to the correct number of significant digits. So if I look at this one, I'm going to draw it as probably the most helpful, right? So I can draw a right triangle where this is 34, 45. And C is the hypotenuse, 10.7 right there, right angle here, okay? And then the sides that I don't know, I can just keep them variables, A, B, capital B. All right, those are what I need to find, A, B, and capital B. Okay, so when you're trying to set this up, try to use what you know. As long as you only have one unknown variable in your setup, you should be able to solve the triangle. So what I'm looking at is this angle, the 34, and let's see if we can find the angle B, right? That would be probably the easiest thing to find at this point because you know the two angles A and B have to add up to 90, okay? So angle B is going to be 90 minus A, right? And because it's in that DMS form, think of this as 89 degrees and 60 minutes minus 34 degrees and 45 minutes. And that's what I'm thinking. You could write that down or just do it in your head. But let's see, 89 minus 34 is 55. And then 60 minus 45 is 15. Okay, so there would be angle B, okay? And notice how we gave it as like this one matches this one, right? They have the same number of significant digits, which is good. Okay, for the sides, I'm going to give them all as 3 significant digits because that's what C looks like. Okay, so next let's try to find little a. Notice little a is opposite the angle, and I have the hypotenuse. So the key players here are opposite and hypotenuse. And if you think about right triangle trigonometry, that's sine, right? Because sine is defined to be the opposite divided by the hypotenuse, right? So I'm going to use that fact. Let's write it down here. Sine theta is opposite over hypotenuse. Okay, and we're going to plug some things in. So it's the sine of 3445, right, equals opposite is unknown, hypotenuse 10.7. All right. And then now you have a little triangle to solve. Okay, so in this, not triangle, equation. So I'm gonna, let's do that color. Let's do multiply both sides by 10.7, right? And then that's gonna be A, right? So A is gonna be equal to 10.7 times the sine of 34 degrees, 45 minutes. All right, and then that's when I'm gonna jump to my calculator to attempt that. Okay. So hopefully you're seeing my calculator pop up, and then I'm just going to type that in, make sure I'm in degree mode, 10.7 sine, and I'm going to put that in as 34 plus 45 over 60. Remember our trick we used from a previous section with dealing with minutes. And this is 6.09, but that 8 rounds that 9 up to a 10. So this is actually 6.10. And that 0, although 6.1 is the same as 6.10, the 0 is important because that's showing that that is 3 significant digits. It's accurate to that number of digits. Okay, 6.10. Finally, we need to get B, and I ran out of room, but that's okay. We'll squeeze it in somewhere. Let's go back to sharing that. So notice, one thing to note is I don't want to use that value that I just found, the 6.10. Okay, let's not use that because it's rounded. So try to use the original values given. Notice that B then is adjacent to that angle that's given, the 34.45. So I'm going to use cosine for that one, right? So I'm going to use the same, I'm just going to do it down here. Sorry, number 9. We'll deal with you later. But cosine of theta is adjacent over hypotenuse. So in this problem, we're going to have cosine of 34.45 equals B over the hypotenuse 10.7. All right. And so it's similar, but I'm just using cosine, right? So B is going to equal 10.7 times the cosine 34 plus 45 over 60. I'll just write it how I'm putting it into my calculator. Right. So that's going to be 10.7. You can try your own calculator too, just to make sure it's working for you. So again, it looks really similar to the first one, just cosine instead of sine. And we're getting 8.79, 3 significant digits. Okay. And we've solved it, all right? So there would be the solution because we found all the sides and all of the angles, okay? Cool. All right, let's try another one. So I'll get back to my handout here. We'll finish off this page and then be done with this video. I'll clean this up later, but for now, you know, maybe you wrote yours better or on a separate piece, but let's go ahead and shrink this down. Let's put you over there for a minute. All right. Okay, so make room for this guy. This triangle only gives 2 sides, right? So I like to draw it first, and I like to use that general triangle, right? So my triangle A is 3.45 and B is 1.83. C is unknown. Angle A and angle B are also unknown. All right, so that's that one. And so one thing you can do is Pythagorean theorem here to get C. So I might do that first because C squared would be A squared plus B squared. Right? Or C is equal to the square root of all of that. Okay, so let's see what that calculates out to be. Get my calculator out. So I would do it just all at once, square root, and then 3.45 squared plus 1.83 squared. So notice I'm trying to do no intermediate rounding. I'm just trying to get it calculated all at once so that I don't have any rounding error. And then this will be 3.91. Okay, there's C. Okay, C is 3.91. Don't use that C to find other stuff. Always stick with the A and the B to get the angles. Okay, so looking back at the image now, let's try to find angle A. Angle A, notice what we're given if we're thinking about angle A here. We have the opposite and we have the adjacent. So which trig function relates opposite and adjacent? If I think back of SOHCAHTOA, it's the TOA, which is opposite over hypotenuse, so tangent. Opposite over adjacent, which is tangent, right? So my next step is tangent is tangent of theta. Let's say A in this case. Tangent of this angle A is its opposite, 3.45, over adjacent, 1.83, okay? So A, if I solve this, anytime you're trying to find the angle, that's when you're going to use tangent inverse, right? And this is what I'm going to put in my calculator. Okay. Back to the calculator. So the way that one looks, let's go ahead and clear all this out. We're doing tan inverse 3.45, all within the parentheses, divided by 1.83. And I'm going to go 1 decimal place, 62.1 degrees. Okay. Okay. Finally, I'm going to get that angle B. And for that, go ahead and just use the fact that those two angles have to add up to 90. So I could just do 90 minus 62.1. 27.9. So that's going to be my B, and I've got it solved. Okay. Okay, so we're doing okay here. So solving a triangle, not too bad. I mean, each one feels a little different because of what you're finding. You might be finding angles, you might be finding sides, you know, but when it says solve, you want to find everything and stick to those trigonometric ratios. SOHCAHTOA really helps. So that's page 1 and 2 of this handout. And in the next video, we'll continue and do some real life word problems. Okay, hope all is well. I'll talk to you in the next video. Bye.